The jungle air hung thick with humidity, as Lieutenant Colonel James Henderson watched his artillery crews prepare for another barrage on Bougainville Island in the late autumn of 1943. What he didn't know was that 20,000 small mechanical devices, each no larger than a man's fist, were about to transform American artillery doctrine forever and turn the Pacific Theater into a chamber of horrors the Japanese High Command had never anticipated. Henderson had been commanding the 105th Field Artillery Battalion for 8 months, but nothing in his training at Fort Sill had prepared him for what these new proximity fuses would accomplish. The devices arrived in unmarked crates labeled with cryptic designations, G-rated fuses, top secret. His superiors had been maddeningly vague about their function, offering only that these fuses would change everything. The Japanese 17th Army, dug into the hills overlooking Empress Augusta Bay, had become masters of defensive warfare. They'd created elaborate bunker systems, spider holes, and interconnected tunnels that rendered conventional artillery fire largely ineffective. Artillery shells would explode on impact with the ground or tree canopy, giving entrenched soldiers precious seconds to take cover. Japanese commanders had calculated that American artillery killed approximately 1 enemy soldier for every 100 shells fired, acceptable losses for defenders who had nowhere to retreat. Major General Harukichi Hyakutake, commanding Japanese forces in the Solomon Islands, had seen this defensive strategy succeed at Guadalcanal and expected it would work again. His intelligence officers had intercepted American radio communications, but found nothing suggesting any technological breakthrough. The Americans would bombard Japanese positions with conventional shells, infantry would advance, and his men would emerge from their fortifications to cut them down with interlocking fields of machine gun fire. It was brutal mathematics that had worked since the trenches of the First World War. Henderson's executive officer, Captain Robert Thornton, supervised the unpacking of the mysterious fuses. Each device contained a miniature radio transmitter and receiver powered by a tiny battery that activated when the shell was fired. According to the technical manual, written in language deliberately obscured to prevent enemy comprehension if captured, the fuse would emit radio waves that bounced off the ground. When the return signal indicated the shell was 20 to 30 feet above the earth, the fuse would detonate the shell, creating an airburst that showered shrapnel downward across a lethal cone. According to documentation from the National Archives referenced in various declassified military studies, the proximity fuse, officially designated the VT or variable time fuse, had been under development since 1940 at Johns Hopkins University's Applied Physics Laboratory. The project was considered so vital that it received priority second only to the Manhattan Project. On the morning of November 5, 1943, Henderson received orders to commence firing. His battery of 105mm howitzers had been loaded with the new shells. The gun crews worked with nervous precision, knowing they were testing something unprecedented. As the first salvo arced through the morning sky, Henderson raised his binoculars toward the Japanese positions 3,000 yards distant. What happened next would echo through military history for generations to come. The shells screamed overhead in a familiar trajectory that Japanese observers had witnessed countless times before. Major Takeshi Yamamoto, commanding the 3rd Battalion of the Japanese 6th Division, stood in his reinforced command bunker carved 15 feet into the hillside. He'd survived the American bombardments at Guadalcanal by recognizing the rhythm of artillery fire, the whistle of incoming shells, the thunderous impacts, the brief pause as American forward observers adjusted coordinates. His men knew to stay down during the bombardment, then emerged to their firing positions before American infantry could close the distance. But this morning, something felt different. The first shell detonated not with the earth-shaking crash of a ground impact, but with a sharp, metallic crack in mid-air. Then another, and another. The sky itself seemed to explode into a horizontal storm of steel fragments traveling at thousands of feet per second. The physics were merciless. Shrapnel falling from above penetrated Japanese helmets, shredded shoulders and backs, and found men in positions that had previously offered protection. Yamamoto's runner, Private First Class Kenji Matsuda, had been crouched in a trench that had weathered dozens of bombardments. The conventional wisdom held that a properly constructed trench with overhead cover would protect against everything except a direct hit. But as the airbursts began their terrible work, Matsuda watched in horror as fragments punched through logs, sandbags, and corrugated metal that had seemed impregnable. The soldier beside him collapsed without a sound, 3 pieces of shrapnel having found their way through gaps in the overhead protection. Henderson watched through his binoculars as the Japanese positions erupted in chaos. Where conventional artillery would have cratered the ground and splintered trees, these airburst rounds created hundreds of lethal bloom patterns in the sky. Each explosion sent approximately 1,500 fragments radiating downward and outward. The mathematical efficiency was staggering. The lethal radius of an airbursting 105mm shell was nearly 5 times that of a ground burst. Artillery calculations that had been refined over decades suddenly became obsolete. Traditional artillery doctrine called for searching fire, walking shells across an area to ensure coverage. But with proximity fuses, each shell covered such a wide area that Henderson's crews could reduce ammunition expenditure by 60%, while actually increasing casualties. Captain Thornton observed the effects through a spotting scope, documenting everything for after-action reports. He watched Japanese soldiers attempt to flee their bunkers, only to be caught in overlapping fields of shrapnel. Those who remained in their fortifications discovered that overhead cover designed to stop shell fragments from ground bursts was nearly useless against fragments falling from above at steep angles. Within 15 minutes, Henderson's battery had fired 200 rounds, a relatively modest bombardment by Pacific theater standards. But the results were catastrophic for the defenders. Japanese radio communications intercepted by American intelligence units descended into panic. Yamamoto attempted to rally his battalion, but company commanders reported casualty rates approaching 50%. Medical personnel were overwhelmed. The carefully constructed defensive positions that had taken weeks to build had become killing zones. What made the proximity fuses particularly devastating was their consistency. Conventional time fuses required artillery crews to calculate the precise moment of detonation based on range, projectile velocity, and atmospheric conditions. Even experienced crews achieved airbursts only 30 to 40% of the time. The G-rated proximity fuses, however, functioned with 90% reliability. Every shell became an aerial mine that detonated at the optimal height automatically. Japanese commanders had no frame of reference for what they were experiencing. Initial reports assumed that American artillery had somehow improved its timing mechanisms, or that forward observers had become impossibly accurate. None suspected that a technological revolution had just rendered their defensive doctrine obsolete. 7,000 miles away in Washington, a small team of scientists and military planners held their breath as coded reports filtered back from Bougainville. Dr. Merle Tuvey, director of the Proximity Fuse program at Johns Hopkins Applied Physics Laboratory, had spent 3 years developing these devices under conditions of absolute secrecy. The stakes were enormous. If the Japanese or Germans captured an intact fuse and reverse-engineered it, the Allies would lose their advantage. If the fuses failed catastrophically in combat, the program might be canceled, and thousands of soldiers would die in conventional artillery exchanges. The development of the proximity fuse represented one of the Second World War's most remarkable engineering achievements. The challenge was creating a radio transmitter and receiver small enough to fit inside an artillery shell, rugged enough to survive the tremendous G-forces of being fired from a cannon, approximately 20,000 times the force of gravity, and reliable enough to function in tropical heat, Arctic cold, and everything between. Tuvey's team had started with a seemingly impossible problem. Vacuum tubes, the only practical electronic components available in 1940, were fragile glass devices that shattered under even modest physical stress. Artillery shells experienced acceleration forces that would instantly destroy any conventional radio equipment. The solution required inventing entirely new manufacturing techniques for vacuum tubes with filaments that could withstand tremendous shock, and envelopes made from specially treated glass. The first prototypes failed spectacularly. Tubes shattered, batteries leaked. Radio circuits produced random false signals that detonated shells prematurely or not at all. Engineers worked 18-hour days, running test after test at the Dahlgren Naval Proving Ground in Virginia. They fired prototype fuses into the Potomac River, mounted them on rocket sleds, dropped them from aircraft, and subjected them to temperature extremes that would have destroyed conventional electronics. According to accounts preserved in the Smithsonian Institution archives, The breakthrough came when engineers realized they needed to abandon traditional vacuum tube design entirely. They developed tiny tubes with heavy-duty filaments mounted on springs, using manufacturing techniques that seemed to violate established electrical engineering principles. The tubes were potted in wax to dampen vibrations. Every component was miniaturized to survive the incredible forces involved. By 1942, the proximity fuse worked reliably in laboratory conditions. But laboratory testing and combat deployment were entirely different challenges. The fuse needed to function after being stored in ammunition ships for weeks, transported through jungle terrain, loaded roughly by exhausted gun crews, and fired from weapons that might be imperfectly maintained under field conditions. The Navy tested early versions during 1942 and 43, using them in anti-aircraft shells against Japanese aircraft. The results were promising, but inconclusive. Aerial targets moved unpredictably, making it difficult to assess the fuse's true effectiveness. But against ground targets, where positions were static and effects could be thoroughly documented, the fuses would prove their worth definitively. Security around the proximity fuse program was extraordinary. Manufacturing took place in facilities cleared by military intelligence. Workers signed non-disclosure agreements threatening imprisonment for security violations. Even the name proximity fuse was considered too revealing. Official documents used code names like G-rated and VT fuse to obscure their function. General Douglas MacArthur's headquarters had requested 20,000 fuses for artillery units operating in the Southwest Pacific Theater. The request was approved in October of 1943, with strict instructions that fuses could only be used where there was no danger of Japanese forces recovering intact examples. Major Yamamoto survived the initial bombardment by remaining deep in his command bunker, but when he emerged to assess the damage, the scene defied comprehension. His battalion had suffered 317 casualties from a 15-minute artillery barrage, a casualty rate that would have required hours of sustained bombardment with conventional shells. Bodies lay in positions that should have been protected. Bunkers that had weathered direct hits from conventional artillery were now death traps, their occupants shredded by fragments that had fallen from above. Japanese military doctrine emphasized detailed after-action analysis. Yamamoto's report, later captured by American forces and now preserved in military archives, described the attack in clinical terms that barely concealed his shock. Enemy artillery achieved unprecedented destruction through shells detonating at uniform height above ground. Casualties occurred in all positions regardless of fortification strength. Recommend immediate investigation of enemy technical capabilities. The report traveled up the chain of command to General Hyakutake's headquarters, then to Imperial General Headquarters in Tokyo. Japanese military intelligence, already stretched thin trying to counter American advantages in code-breaking, aircraft carriers, and submarine warfare, now faced evidence of another technological breakthrough. But without physical evidence, an intact fuse to examine, they could only speculate about the mechanism. Some Japanese officers theorized that American forward observers had become extraordinarily skilled at adjusting time fuses. Others suggested that Americans had developed new optical ranging equipment that allowed precise calculation of airburst timing. A few suspected an electronic innovation, but couldn't imagine how vacuum tube technology could survive artillery launch forces. Lieutenant General Hitoshi Imamura, commanding the 8th Area Army from Rabaul, ordered defensive doctrine changes. Japanese troops were instructed to dig deeper bunkers with multiple layers of overhead protection. Spider holes were to be covered with heavier logs and more sandbags. Trenches were to be abandoned in favor of individual fighting positions spread over wider areas to minimize casualties from single airbursts. But these adaptations required time, materials, and labor, resources that Japanese forces in the Pacific increasingly lacked. American submarines had strangled Japanese supply lines. The naval defeats at Midway and the Philippine Sea meant that reinforcements and construction materials rarely reached forward positions. Japanese soldiers were already malnourished, short of ammunition, and stretched to breaking point. Building deeper, stronger fortifications was theoretically sound, but practically impossible for many units. On December 10, 1943, American forces launched another offensive on Bougainville, this time with 8 artillery battalions equipped with proximity fuses. Japanese defenders of the Numa Numa Trail found themselves subjected to rolling barrages that turned the jungle canopy into a steel rain. Captain Hiroshi Tanaka, commanding a company of the Japanese 38th Infantry Regiment, recorded in his diary, later recovered by Australian forces, that the bombardment was unlike anything witnessed in China or previous Pacific battles. Men who survived Guadalcanal became casualties within minutes. No defensive position offers safety. The psychological impact was perhaps as significant as the physical casualties. Japanese soldiers had learned to endure conventional artillery through a combination of discipline, fatalism, and the knowledge that properly constructed fortifications offered reasonable protection. The proximity fuses shattered that confidence. Every artillery barrage became a lottery where survival seemed random. Soldiers who had weathered months of combat began showing signs of shell shock after a single sustained bombardment with air-bursting rounds. American intelligence officers noticed changes in Japanese radio communications. Messages became more desperate, requests for medical supplies more urgent. Prisoners of war described widespread fear of American artillery that exploded in the trees and could kill men underground. By early 1944, American artillery battalions across the Pacific Theater had received proximity fuse, and commanders were developing new tactical doctrines to exploit their capabilities. Colonel Harold Mitchell, commanding artillery for the 27th Infantry Division preparing for the invasion of Saipan, recognized that the fuses fundamentally changed the relationship between artillery and infantry. Traditional combined arms doctrine required infantry to advance immediately after an artillery barrage ended, catching defenders before they could return to their firing positions. This created a dangerous transition period where artillery fire had to cease to avoid friendly casualties, giving defenders time to recover. But proximity fuses were so effective at suppressing enemy positions that Mitchell experimented with extending bombardments until infantry were within 200 yards of Japanese lines, far closer than previously considered safe. The mathematical calculations were straightforward, but represented a radical departure from established practice. With conventional ground-burst shells, fragments would scatter in all directions, including back toward friendly forces. But air-bursting shells directed most fragments downward and forward, creating a safer zone behind the burst. Artillery officers with slide rules and trigonometry tables calculated safe zones that allowed friendly forces to operate much closer to impact areas. At the Saipan landings in June of 1944, American forces put these calculations to the test. As Marines waded ashore at Beach Blue 1, artillery batteries mounted on landing craft offshore fired proximity-fused shells over their heads into Japanese defensive positions. The timing was precise. Shells detonated above the Japanese 3rd Independent Mountain Artillery Regiment's positions while Marines were still 250 yards from the beach, far closer support than conventional artillery could provide. Lieutenant Yoshio Nakamura, commanding a machine gun section overlooking the landing beach, had orders to wait until American forces were fully committed before opening fire, standard Japanese defensive doctrine. But the air-bursting shells found his position before he could execute those orders. His entire section was killed or wounded before firing a shot. Similar scenarios played out across the beachhead. Japanese forces that should have inflicted heavy casualties during the vulnerable landing phase were suppressed or destroyed by artillery fire that conventional doctrine said couldn't be employed so close to friendly forces. The Battle of Saipan, according to military historians and documentation from the Naval History and Heritage Command, marked the first time American forces fully integrated proximity-fused artillery into amphibious operations. The results were dramatic. Marine casualties during the landing phase were 40% lower than predicted. Japanese defenders reported that they were unable to maintain firing positions during the initial American assault. Japanese commanders on Saipan tried new counter-tactics. They moved defensive positions deeper inland, beyond the range of naval artillery. They dispersed forces to minimize casualties from individual airbursts. They attacked at night when American artillery observers had limited visibility. But each adaptation had costs. Moving positions inland meant yielding the beaches without resistance. Dispersing forces made coordinated defense more difficult. Night attacks were risky and resulted in high casualties from American small arms fire and pre-registered artillery coordinates. Admiral Raymond Spruance, commanding the Fifth Fleet during the Marianas Campaign, noted in his after-action report that proximity fuses had materially contributed to the success of operations and significantly reduced American casualties. He recommended their use be expanded to all artillery units operating in the Pacific. By summer of 1944, American factories were producing proximity fuses at a rate of 40,000 per month. The National Defense Research Committee, which had overseen the fuse's development, approved their use in the European theater, though with restrictions to prevent capture by German forces. The proximity fuse's introduction to European combat came during the Battle of the Bulge in December of 1944, when German forces launched their last major offensive through the Ardennes forest. American artillery units, many equipped with proximity fuses for the first time, found themselves in desperate defensive battles against massed German armor and infantry. On December 23, 1944, near the Belgian town of Bastogne, Lieutenant Colonel William Seeley's Artillery Group Alpha found itself supporting the surrounded 101st Airborne Division. German forces had encircled the town, and conventional artillery fire had proven insufficient to break up German infantry attacks that came in dense formations, a tactic designed to overwhelm American defensive positions through sheer numbers. Seeley had recently received a shipment of proximity fuses, with instructions to use them only when absolutely necessary, and when capture by German forces was unlikely. As German infantry massed for another assault on the town's perimeter, Seeley made the decision to employ the fuses. His 155mm howitzers fired time-on-target salvos, coordinated fire where shells from multiple batteries arrived simultaneously, all fused for airburst. The effect on massed German infantry was catastrophic. Oberst Heinrich Fischer, commanding the 77th Volksgrenadier Regiment, had organized his forces for a traditional infantry assault, with companies advancing in relatively tight formations to maintain command and control in the dense Ardennes forest. When American shells began detonating 30 feet above his formations, casualties were immediate and severe. Fischer's after-action report, captured after the war, and now in the U.S. Army Military History Institute archives, described tree bursts of unprecedented accuracy and devastating effect. What Fischer didn't know was that the shells weren't bursting against trees at all. They were detonating based on radio proximity to the ground, creating perfectly timed airbursts regardless of terrain or weather conditions. The distinction was technical, but militarily significant. Conventional time-fused shells required careful calculation and often failed to achieve optimal burst height in forested terrain. Proximity fuses worked with mechanical precision in any environment. German military intelligence, like their Japanese counterparts, struggled to understand what they were facing. Initial reports assumed Americans had perfected timing mechanisms for tree bursts, but as more evidence accumulated, including the recovery of shell fragments containing unusual electronic components, German scientists began to suspect something more sophisticated. In January of 1945, German forces recovered several proximity fuses that had failed to detonate. The devices were rushed to technical intelligence units, then to research facilities in Germany where scientists attempted to reverse engineer them. What they found astonished them. Miniaturized vacuum tube radios small enough to fit in an artillery shell, manufactured to tolerances that German industry, strained by years of war and Allied bombing, could not replicate. Dr. Werner Brascher, a German electrical engineer assigned to analyze captured fuses, wrote in his report, later recovered by Allied forces, that the devices represented an engineering achievement of the highest order, combining advances in miniaturization, ruggedization, and mass production that our industry cannot match in present circumstances. He concluded that Germany lacked both the manufacturing capability and time to develop equivalent technology before the war's end. German defensive doctrine adapted as much as circumstances allowed. Troops were ordered to spread out during artillery bombardments, reducing casualties from individual airbursts. But spreading out made command and control more difficult and reduced the density of defensive fire that German tactics relied upon. Once again, the proximity fuse forced tactical compromises that weakened defensive effectiveness. The proximity fuse's most significant test came during the assault on the German Siegfried Line in early 1945. The fortifications, officially called the West Wall, consisted of hundreds of bunkers, dragon's teeth anti-tank obstacles, and interconnected defensive positions stretching from the Netherlands to Switzerland. German commanders had spent years perfecting these defenses, confident that they would delay Allied advances for months. Major General J. Lawton Collins, commanding the 7th Corps, planned a methodical assault on a section of the Siegfried Line near Aachen. His artillery commander, Brigadier General Charles Hart, had access to virtually unlimited supplies of proximity-fused ammunition and orders to use it liberally. The assault began on February 8, 1945, with a bombardment that transformed military doctrine. Hart's artillery plan called for time-on-target missions that would place simultaneous airbursts over German positions in a rolling pattern that moved forward at a predetermined rate. Infantry would advance behind this moving curtain of explosions, remaining so close to the bombardment that German defenders would have no time to recover between the end of artillery fire and the arrival of American troops. The technique, later named walking fire, or creeping barrage with proximity fuses, required extraordinary coordination between artillery and infantry commanders. Forward observers adjusted fire in real time, while infantry maintained advance rates synchronized with artillery movement. The margin for error was slim, advance too quickly, and infantry would walk into their own artillery fire, too slowly, and German defenders would have time to recover. German defenders along the Siegfried Line had prepared for conventional artillery tactics. Bunkers were designed to withstand direct hits from the largest Allied guns. Overhead cover on trenches was heavy enough to stop shell fragments from ground bursts. Communication trenches allowed defenders to move between positions while protected from observed fire. But none of these preparations addressed air-bursting shells that showered fragments from above with mechanical precision. Unteroffizier Karl Becker, a veteran of the Eastern Front commanding a machine gun position in a Siegfried Line bunker, recorded his experience in a letter captured after his position was overrun. The American artillery was unlike anything at Stalingrad or Kursk. Shells exploded above the ground with perfect timing, creating a steel rain that found every gap in our defenses. Men who survived years of Russian bombardments became casualties in minutes. The assault on the Siegfried Line section near Aachen achieved penetration in 4 days, operations that pre-war planners had estimated would require 4 to 6 weeks. German casualty rates were double those of comparable defensive actions earlier in the war. Post-battle analysis revealed that proximity fuses had increased artillery effectiveness by a factor of 4 to 5 compared to conventional ammunition. By March of 1945, as Allied forces crossed the Rhine and advanced into Germany, proximity fuses had become standard ammunition for American and British artillery units. German forces, retreating toward Berlin, faced artillery that could strike them in any defensive position with terrifying effectiveness. The war in Europe ended on May 8, 1945, and in the Pacific on August 15 of the same year. In the aftermath, military analysts examined proximity fuse performance across hundreds of engagements. The statistics were remarkable. Artillery equipped with proximity fuses achieved casualty rates 3 to 5 times higher than conventional ammunition while using 40% less ammunition. In defensive operations, proximity-fused artillery broke up enemy attacks with unprecedented effectiveness. In offensive operations, it suppressed enemy defenses more completely than any previous technology. The human cost behind those statistics was staggering. Japanese and German forces had suffered casualties from proximity-fused artillery that exceeded all pre-war predictions. Medical records captured after the war showed that wounds from air-bursting shells were typically more severe than those from ground bursts, as fragments struck soldiers from above, hitting heads, shoulders, and backs. Survival rates for soldiers caught in proximity-fused barrages were significantly lower than for conventional artillery attacks. After Japan's surrender, American intelligence officers interviewed Japanese commanders about their wartime experiences. General Tomoyuki Yamashita, who had commanded forces in the Philippines, stated in his debriefing that American artillery with tree-burst fuses had been one of the most significant factors in Japan's defeat in the Pacific. He noted that Japanese defensive doctrine, refined over years of war in China, had been rendered obsolete by technology his forces couldn't counter. The proximity fuse remained highly classified until 1947, when details were finally released to the public, The revelation that American artillery had employed sophisticated radio-controlled fuses throughout the war's final years astonished both the scientific community and the general public. Popular Science magazine ran a feature article explaining how miniature radios in artillery shells had revolutionized warfare without the enemy understanding what they faced. The fuse's development had cost approximately $27 million. Expensive by wartime standards, but a fraction of the Manhattan Project's $2 billion price tag. Yet many military historians argue that the proximity fuse saved more American lives than any other single technology of the Second World War. By making artillery dramatically more effective, it reduced the need for costly infantry assaults and shortened battles that might otherwise have lasted weeks or months. Post-war analysis calculated that proximity fuses had killed or wounded approximately 60,000 to 75,000 enemy soldiers, beyond what conventional artillery would have achieved. More significantly, by breaking up enemy attacks and suppressing defenses more effectively, the fuses allowed American and Allied forces to advance more quickly and with lower casualties. The number of Allied lives saved through reduced combat exposure was estimated at 15,000 to 20,000. The technology spawned immediate evolution. By the Korean War, proximity fuses had been refined and improved. By Vietnam, they were standard equipment. Modern artillery still employs descendants of those original G-rated fuses developed in the laboratories of Johns Hopkins University in the early 1940s. Dr. Merle Tuvey, who had led the proximity fuse program, received the Medal of Merit in recognition of his work. In his acceptance speech, he reflected on the project's moral complexity. "We created a weapon that undoubtedly killed many human beings, but we also created a weapon that ended battles more quickly and saved the lives of young men who would otherwise have died in prolonged combat. I cannot resolve that paradox. I can only say that we did what our nation asked of us in a time of existential threat." The proximity fuse represented more than just a technical achievement. It demonstrated that scientific innovation could fundamentally alter warfare's calculus, that small groups of dedicated engineers working in secrecy could create capabilities that shifted the balance of power between nations. The Japanese and Germans never expected that 20,000 small devices would transform American artillery from a blunt instrument into a precision system that dominated the battlefield. In the end, the proximity fuse did exactly what its developers intended. It made American artillery devastatingly effective, saved Allied lives, and helped bring the war to a faster conclusion. The steel rain that fell from skies over Bougainville, Saipan, Bastogne, and 100 other battlefields represented human ingenuity applied to humanity's most terrible endeavor, war itself. That the fuse succeeded so completely speaks to both the brilliance of its creators and the tragedy of the circumstances that demanded its creation.